Good day and welcome to another physics lesson. Today we'll be looking at Pascal's principle. Pascal's principle is an offshoot of pressure in fluids. So we'll be looking at what that is today. I hope that by the end of this lesson, you will have learned quite a few things. So now let's look at the objectives that we have for today's lesson. First, we will state Pascal's principle. We will look at some of the applications of Pascal's principle. We will perform simple calculations, and then we'll be able to see how this applies to our daily living. So, what is Pascal's principle? This is a principle that states that the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the vessel containing the fluid. What this is saying in essence is that when you apply pressure at a point in a fluid, the pressure you apply at that point will be transmitted uniformly to every other point in the vessel where you have the fluid. So if you apply pressure at a point, say in a tire, you apply pressure on the tire valve. Now, the pressure that you apply there will spread uniformly across every section of the tire, every area of the tire, and even it will be applied along the walls of the tire uniformly. That is what Pascal's principle says. So in essence, Pascal's principle is just talking about the undiminished transmission of pressure from one point of application to different points in a particular fluid. Pascal's principle finds application in the hydraulic press. The hydraulic press is one system that is used for different things, particularly to lift heavy equipment. So when we say that this pressure you apply at a point will be transmitted uniformly, that means, for instance, that if you look at the diagram on your screen, the pressure you apply in will be the same pressure that will be exerted all through every part of that fluid in the vessel, in the press, and then to be also equal to the pressure out. Let us not forget that already we know that pressure is equal to force divided by area. So the pressure you apply in, that's the force you apply on the input piston divided by the area of that piston. That pressure you get from there will be the same pressure you will find at every other point in the hydraulic press. That is why pressure in is equal to pressure out. And if pressure in equals pressure out, what it means is that force in over area in is equal to force out over area out. Or you could say that input force divided by the input area is equal to the output force divided by the area of the output piston. Now let's look at the makeup of the hydraulic press. The hydraulic press consists of two cylinders of different diameters. Now, different diameters essentially means that the two cylinders would have different areas. Now, these different diameters are joined by a connecting tube. You could see that on the diagram on the previous slide. Now, a tight piston is fitted to each cylinder. The piston with a small cross-sectional area is used to exert a small force. Now, this pressure you get from there, that's a small force divided by small area. The pressure you get from there is transmitted through the connecting pipe to the larger cylinder, which has a piston of larger area and hence a larger force. But since pressure is force over area, by the time you do force over area for both the input and the output piston, you will get the same values for pressure. As I said earlier, the hydraulic press finds use in lifting heavy equipment or heavy machinery. It is used in the hydraulic jack where we use it to raise heavy cars. It is used to compress bags of cotton or wool in the hydraulic press. Now, let us look at how this works. Since the hydraulic jack essentially is a kind of machine, then it must have something called mechanical advantage. Now, the mechanical advantage of a machine is the load divided by effort. Don't forget that load is a force. Load is the output force. That is the load that you want the hydraulic press to help you lift. In this case, it could be the weight of the car. And then the effort is the input force. That's the force that you are exerting on the press. So if mechanical advantage is load over effort, and we said that the load is the output force, effort is the input force, going back to the formula for pressure in an hydraulic press, that will give us output area divided by input area. Now, we also know that velocity ratio of a machine is already defined as distance moved by effort over distance moved by load. So, the distance moved by effort divided by the distance moved by load. If we do that from the formula of the hydraulic press, it will give us the output area divided by the input area. And here we use that to get the velocity ratio of the hydraulic press. Here we have a very simple diagram and an exercise to explain how this works in theory. We have the input area divided by the input pressure equal to the output pressure. Input pressure is input force divided by input area. Output pressure is output force divided by output area, and both of them are equal to each other. So look at the diagram. You are given the data that you need. You were told the diameter of the press of the cylinders of the press. You have the 4 centimeter and 12 centimeter, and we also have the weight you want it to lift. That is the output force. Now we are looking for the input force. So all we need to do is to make input force subject of the formula, and then of course we find our areas. Area, as we know, is pi r squared. That is circular surface area. That is pi r squared. R meaning diameter. R meaning radius. That means you have to divide the diameter by 2 to get the radius. So after getting your area for both pistons, you can now put the areas in the formulas, and then you find your input force. If you do that well, you find that your input force is 444 newtons. So that means that for this setup, you need an input force of 444 newtons to be able to lift a car of 4,000 newtons weight. Another application of the hydraulic brake system is in the car brakes. We have the brakes in automobiles. They use the hydraulic principle to transmit pressure from the foot pedal to the brakes. So this slows down each wheel equally and reduces the danger of skidding. So when you apply the brakes on a moving car, all the 4 wheels or 16 wheels, as it were, would feel the pressure equally, so that they all begin to reduce their speed uniformly, not one reducing faster than the other. Because if one reduces its speed faster than the other, then there could be a risk of skidding. But that is taken care of in the hydraulic brake system. Let us look at a solved example of this. We have a large cylinder which has a length of 20 cm, a radius of 20 cm rather, and then we have a small cylinder that has a radius of 5 cm. Now, a force of 100 Newton is applied on the small piston. Calculate the force on the large piston. Just as we did earlier, force over area inwards is equal to force over area outwards. Or if you like, force over area for small piston equals to force over area for large piston. So you just slot in all the values. Don't forget that you must find your area. What you have here is the radius. You must use the radius to find the area for each cylinder, and then you get your force, the force that you are looking for on the large piston. So in this case, looking for our area, we must convert both centimeters to meters first, and then find the area. So the area of the small piston gives us 0.00785 meters squared. while that of a large piston gives us 0.126 meters squared. So slotting in the two areas and then looking for the F that we need to find, that F will give us 1605.10 newtons. Now the B part of the question asks us to find the distance moved, the volume of the large piston. Now when the small piston moves through 0.4 meter, you find the volume. The small piston moves through 0.4 meter, that is the height moved. You find its volume. Volume is area times distance. We already know its area. Then just multiply that area by distance. Recall that volume is essentially area times height. Height in this case is the distance that was moved downwards by the small piston. So we'll find our volume for the small piston. Now, since the same volume must be transmitted, because when your small piston moves down with volume, the same volume will be the volume of the large piston that will be moved upwards. So the volume will be the same. So that means that the volume of the large piston will also be 0.00314 meter cube. Now we have the area of the large piston as well. That's 0.126. Then we can just find the distance moved by the large piston. By dividing the volume by the area, we find the distance, and that gives us 2.5 centimeters. Here we have some applications of atmospheric pressure and liquid pressure. This has to do with a topic that we looked at, pressure. We looked at pressure. There's a video on pressure also on this YouTube channel. You may try to check it out. So, some of the places where atmospheric pressure finds use is in our sucking of drinks, for instance. You're sucking through a straw. You're taking a drink through a straw. When you suck on the straw, the volume of your lungs is increased and pressure is reduced in the lungs and mouth. Then the atmospheric pressure acting on the surface of the liquid will then be greater than the pressure in the mouth. So it's able to draw up the liquid. Also, we have the siphon. The siphon is a flexible hose used to drain liquid from a tank or reservoir. And for the siphon to work, one end of the tube must be lower than the surface of the liquid to be drained. Then the pressure at the surface of the liquid to be drained at that end of the liquid is equal to the atmospheric pressure, while the pressure at the other end is greater than atmospheric pressure. So the liquid is then able to flow out from the lower end due to this higher pressure once the hose is primed. The syringe is also another useful application of atmospheric pressure and liquid pressure. To draw liquid into a syringe, the piston of the syringe is drawn upwards. When you do this, the pressure in the syringe is reduced because you have created more space within the syringe. So the molecules there are not vibrating as fast as they were. They now have more area to cover, and then they have a reduced rate of collision. So this reduces pressure in the syringe. Now the atmospheric pressure on the surface of the liquid is then higher than the pressure in the syringe, and that pushes the liquid into the syringe. So those are some of the applications of atmospheric pressure. Now we have assignments that have to do basically with the topic we just looked at, Pascal's principle. I would advise that you do this work. Also, a related video that you need to see that will make this work easier for you is that of pressure. As I said, it's already on this channel. Please check it out. In addition to this, you'll be able to do these assignments that we have here. Peradventure, you have comments, questions, gray areas that you seek further clarifications on, please do not hesitate to drop a comment just under here, and I will respond to that. Hope this lesson has been of use to you. Hope you've learned one thing or the other. Thank you. Hope to get across to you in another lesson.